Hello, all, and welcome to the second part of our big, long four-part lecture on limits. Today, we're going to talk about limit properties. This will actually go fairly quickly. Um, there's not a whole lot of limit properties really to look at, but they are important because you'll kind of use them subconsciously almost all the time. So having them nailed down and knowing exactly what you can and can't do with limits is important. So we've seen some examples of limits before. I've been giving you two parts of a limit. I've said, hey, we've got a limit as x approaches some value. And here I'm just going to leave that value general and call it c. But on worksheets and problems that you've been doing, you've got some value there. You also have some function here. And right now I'm just going to leave that general. I'm going to call that function f. And when you evaluate that limit, you end up getting a number out. You get an answer. You get 7, or you get 22, or -8. You get some number out. And again, I'm just going to leave that general. I'm going to call that a. So let's just say that if I ever, in the future slides, if I ever show you this limit of f of x as x approaches c, just for shorthand, we're going to call that a, because I don't really want to have to go and write out limit as x approaches c of f of x every single time. I can just write a instead, and that'll be our shorthand for it. And the same thing goes for here. I'm just considering a different function than f. I'm going to consider a function I'm going to call g, and the limit would be presumably different. It doesn't have to be, but it could coincidentally be the same. But we're going to just call that b so that I don't have to write out limit of g of x as x approaches c and just keep writing that over and over. So let's go ahead and move on to the first algebraic property. And this is what we'll call the constant property. So in this right here, k is just any constant value. And so if I ever gave you a limit where you had the limit of a function being multiplied by a constant, what you are allowed to do is you're allowed to just sort of pull that constant out front. And that's what I've done right here. I've taken this k and I've pulled it out front, and now I just have that limit of f of x. And like we said on that last slide, I'm going to call that a right there, just for shorthand. And so basically, if you knew the limit of f of x, and let's just do an example here. Let's say that we know off the top of our heads, hopefully, that the limit as x approaches 4 of x squared. We know that that's 16. We can just take that 4, we can do a direct substitution. Every time we see a limit, we start off right with direct substitution. We're going to take that 4, we're going to plug it in, and we're going to get 4 squared, which is 16. But now what I'm telling you with this constant property is what happens if I give you this limit. Limit as x approaches 4 of 3x squared. Well, using this constant property, what you can recognize is, oh, this 3 is it's just a constant that I'm multiplying my function x squared by. So what I'm allowed to do is I'm allowed to pull that 3 out front of the limit. And I can say that this is equal to 3 times the limit as x approaches 4 of x squared. And we just did that limit right there. This guy here, we just calculated that. So we know very quickly that that's 16. And then I can just multiply it by 3. So again, like I mentioned before, you probably won't even think about this a whole lot. You'll probably do this fairly subconsciously. But it's good to know you're allowed to pull constants out of limits if you want to. Yeah, so it's the constant property. Let's keep on going to the sum and difference property. And this is a key one here. So let's say that you have a limit of two functions that are either added or subtracted together. So for an example, maybe I give you limit as x approaches 3 of x squared plus square root of x. What you're allowed to do here is you're allowed to split this limit into two different limits. And again, you probably won't even really think about this as you're doing it. You're probably doing this fairly subconsciously, but sometimes it's nice to just split these limits up so that you can think about them sort of one at a time without getting, overwhelmed by, how many limits there are. And so in this case, I could just look solely at this guy. I could answer that, and then I can separately look solely at this guy and just answer that. And whatever those answers are, I can take those and I can add them together. And if I actually just do that, let me write that out here. I would end up with 9 plus the square root of 3. No simplification there. I can't really do anything with that square root of 3. That's fine. This will just be our answer. We'll just leave it right there. But the sum and difference property tells us that if I have that limit of two functions added together, I can split them into two different limits added or subtracted together. So let's go ahead and move on next to the product property. And this is something that a lot of people wouldn't think actually works. It's a little bit tough to prove, but in fact, it does actually work, and we'll call it the product property. And so if you have if you have one limit with two functions and those functions are being multiplied together, you can separate those into two different limits. And that can be very helpful, especially because we've mostly been doing limits graphically so far. Let's say I gave you a limit that was written as such: limit as x approaches 4 of x squared. Well, let's say this. Yeah, I'll just say x squared times square root of x. When I look at that, I don't know what a graph of x squared times square root of x looks like off the top of my head. That's something that would be tough to graph. I'd probably have to use a calculator or a computer to graph that. And so I might kind of be stuck if I wasn't really comfortable with doing my direct substitution at this point. But what I could do is I could use this product property to split this limit into two limits that are multiplied by each other. And if I do that, now you can see that I could graph either of these pretty easily if I wanted to. And I also could just do my direct substitution. I could just take the 4 and I could plug it in. But you're allowed to split these up and multiply your individual answers. So here we have 16 times root 4, which would be 16 times 2, which would be 32. And that'd be our final answer. And there we go. We got the product property that you can split limits along a multiplication. Very similarly, we have the quotient property, and it says basically the same exact thing as what we just saw, but it says it with division. And so if you have two functions that are being divided by each other, then you can split them up, and that's all right. That's all right and okay. And again, this would work really well if I gave you something of this form. If we look at this function here, I don't know how to graph x plus 1 over square root of x off the top of my head, but I'm allowed to split this limit up. Top and bottom. And then I'm on my way, and I can just do my direct substitution. Or if I'm not comfortable with direct substitution, I could graph each of them separately, because x plus 1 is easy to graph, and root x is easy to graph each on their own. I'll go ahead and leave my answer just written here. I know a lot of times we don't like to have radicals in the denominator, but for now I'm okay with that. That's fine. And there we go. We've got our answer. We're allowed to split limits along a division symbol. And the last limit property that we'll see is the exponent property. Again, a seemingly, well, one that probably seems like you can't really do it, but you are allowed to. If you have a function and it's being raised to a power, you can sort of pull that power out and take the power of the entire limit. So this, I'll do this with an example. Let's say I had something like limit as x approaches 3 of e to the 2x. What you could recognize here is that you could actually rewrite this as e to the x squared. And then let me even just be very redundant and put even more parentheses and brackets just to make it very clear. That e to the x that's being squared, that's all in this limit. But now with this exponent property, I can take the entire limit and I can basically just sort of pull that squared out. And there we go. Now I can just do the limit of e to the x, and then I can evaluate that. I can then square it. That might be helpful because e to the x is a little bit easier for me to graph than e to the 2x. So, you know, I've saved myself some work on the graphing there. Let me be very clear though, on basically all these examples that I've been going through, you would probably just take this and do a direct substitution. You would just take 3 and you would just plug it in where you saw an x. Here, you probably would have just taken 5 and you would have plugged it in where you saw these x's. And then here, you would have taken a 4 and just plugged it in. So I use these sort of simple examples just so we don't get overwhelmed with all these properties that we're seeing. Like I've said, you're probably going to subconsciously use these. You're not even going to be thinking about it. A great example is that constant property that we saw. If you see a limit of 3x squared, you're probably not going to think to yourself to pull out that 3. You're just going to take the 4 and you're going to plug it right into the x, and then you're going to have 3 times 4 squared, 3 times 16, 48. You'd be done and on your way. But these limit properties are there for you in case they make sense to use. And we've got all of them from the constant property to the sum and difference property to the product and quotient properties, and then the exponent property last. And I'm going to go ahead and leave it at that. That's all of our limit properties. So we'll get comfortable working with those a little bit more, and I'll see you next time.